Hello, and welcome to section 5.4, the indefinite integral and the net change theorem. So this section builds on what we've seen in the previous section. Remember antiderivative, performing the inverse process of differentiation on a function, and we saw that there was a connection between the derivative and the result of a definite integral. And that's what the fundamental theorem of calculus showed us. So in this section, really, we're going to go back to the antiderivative and just give it a name called an indefinite integral. So this is really something that's in practice, the homework problems are the same things that you've done before in section 4.9 when you found the antiderivative, the general antiderivative, but now we have notation for it that we call the indefinite integral. So let's look at that. So an indefinite integral is going to be written like this, where you don't have limits of integration. So let's look at an indefinite integral versus a definite integral. So remember in last section, a definite integral is the area under a curve between A and B, 2 points on an interval on the x-axis, and it's a number, right? Whereas an indefinite integral is just an antiderivative. It's a general antiderivative. So we need to remember to add that constant of integration every time we see an indefinite integral. And so like antiderivatives, it's a family of functions translated by a constant. So we saw something like this in section 4.9, except we would say, call it an antiderivative, and we didn't have any notation like this to describe what we were doing. We had to say in words, take the antiderivative. Now we have some notation and we know what we need to do. So again, remember that this constant of integration is just translates that definite integral up and down, because when you do take the derivative of it, you're going to get the same value. So the first example we're going to look at to evaluate this integral, well, that's the same process as finding the most general antiderivative. So we'll multiply the 2 to the t through. We'll break it up into two integrals. And we use the antidifferentiation formulas for the exponential function. And the integral of 2 to the t is 2 to the t over ln of 2. The indefinite integral of 10 to the t is 10 to the t over ln of 10. And then we add that constant of integration. So we've done these types of problems before. Example 2, again, find the indefinite integral. Now we don't have an antidifferentiation or an antiderivative formula for this, but with a lot of trig integrals, you can use an identity or simplify the integrand. And if we use the identity for sine 2 theta in the numerator, we can cancel the sine theta factors and find the indefinite integral of 2 cosine theta, which is just 2 sine theta plus c. So now on to the net change theorem, and it's really just another way of stating the fundamental theorem of calculus, the second part of it. So remember, the fundamental theorem of calculus told us that for a definite integral, we could find the antiderivative of the integrand and then evaluate it at the limits of integration and subtract those, where f was any antiderivative. So since capital F is an antiderivative of this integrand f, that means that f prime equals f. So we can just rewrite this here. We replace the f of x, lowercase f of x, with capital F prime of x, since it's its antiderivative. And all this is saying is the integral of the derivative of a function is just that function evaluated at the endpoints and taking the difference. So this is useful when you are given a rate. So look at f prime of x here. Since it's a derivative, you know it's the rate of change of the function capital F. So thinking of the fundamental theorem of calculus this way, this is helpful in finding how functions have changed when you know the rate of the function.